Okay, so we've done the electric field for a point charge, which also works for a sphere. Looked at the electric field for a finite length line of charge. Your book derives a couple more. We're not going to go through the derivation. For a ring, so if you have a wire bent around into a ring, if you want to find the electric field, the equation they give you is only along the axis. So if you imagine the axis coming out from the center, so the equation depends upon how far away you are from the axis. We end up with K is our regular constant, Z being the axis, so coming out of the board, Z being how far away you are from the plane of the ring, Q being the total charge spread around the ring, and big R being the radius of the ring. This one's actually pretty easy to integrate. You do it the same way we've been doing the lines of the rods and the lines of charge. You would write your dq is equal to q over L times ds in this case. The nice thing is you don't actually end up having to integrate anything because nothing's changing. So all of the x and y components of the field cancel out and the field ends up only being in the z direction. So a piece of the ring on this side creates an electric field going away from it. This one away from it, so those x components cancel, leaving you with just z. So that is the net electric field ends up pointing away from the ring. If this, instead of just being a ring, so by a ring I just mean a nice thin little wire bent in a circle. If this was solid, so if it was a whole disc, so it's still round, it still has a radius of r, but there's charge spread over the entire disk. So it's a solid object. So it's more like a cylinder. The equation ends up being again, Z is along the axis coming out of the board. R is the radius of the actual disk. Eta, remember eta here is the surface charge density. That's charge per area. So there's charge spread over the entire area of the disk. Epsilon naught is our other constant, the 8.85 times 10 to the negative 12. Notice with this equation, if Z is really small compared to R, meaning if you're really close to this disk, this term actually goes to 0 because you have a small number over a big number. As long as Z, if Z is a lot smaller than R, this term goes to 0. And we get E is equal to eta over 2 epsilon naught. So as long as you are close to the center of that disk, then the electric field actually ends up not depending upon how far away you are. But that's only if you're close compared to the size of the disk. Another, this would be so we could say it was an infinitely large disk. It will work as well if it doesn't have to be round. It can be a plate, it could be square or rectangular. As long as we are close enough to the disc or the plate, so as long as that distance is very small compared to the dimensions of the plate, this equation for electric field will work. Works out quite nicely because it turns out that it's very common to have really fairly large plates in comparison to how far away you want to know the field. So this equation is actually used quite commonly. For example, a common circuit element that we'll talk about is a capacitor. The capacitor, the general makeup, though they're not all made the same way, but a general makeup is two plates parallel to each other. So we're looking at them from the side. So one big plate, a second big plate. In the electronic circuit, they become oppositely charged. So one ends up being positively charged, which induces the other plate to have the same charge density, only it's negatively charged. So if one is positively charged and the other is negatively charged, there's going to be an electric field. For example, what will the electric field look like due to this positive plate over here? Which direction will it be in? So it's outwards, outwards, and it's creating a field over here as well. This plate, since it's negatively charged, its electric field is inwards, towards it. So what happens is outside, as long as this distance in here is very small compared to the actual dimensions of the plates, as long as that distance is small compared to the dimensions of the plates, this equation will work fine for each plate individually. Okay. That means these are going to cancel, and these are going to cancel, because they're in opposite directions, same magnitude. But these two are in the same direction. So the total electric field for the capacitor will be E for the positive plate plus E for the negative plate. But keep in mind they're in the same direction. So in the case, the example I've drawn on the board, it's in the I-hat direction. So we're going to take the absolute values of the charge density and put our own directions on it. If you used actual values of the charge density, one being positive, one being negative, when you added it, what would you get? You get 0, they'd cancel. Which isn't the case. They're in the same direction. They're adding together. So we use the absolute value of the etas. Since they're the same, we get 2 eta over 2 epsilon naught in the x direction in this case. So eta over epsilon naught in the x direction ends up being the electric field for the capacitor. So that's the strength of the electric field between the two plates, is eta over epsilon naught. Now, to be a capacitor, they have to have the same charge densities. Okay. For example, let's say we have two plates that are parallel to each other. One has a surface charge density of 40 nanocoulombs per meter squared. The other one has a surface charge density of negative 60 nanocoulombs per meter squared. This would not be considered a capacitor. A capacitor, they have the same charge densities. One positive, one negative, but the values need to be the same. So we cannot, in a case like this, let's say we want to find the electric field over here in the center. cannot use this. Okay? Yes?
Isn't usually capacitor, the reason why they're the same is because one gets stuff pulled from one side to the other side,
Yes.
so
Yeah.
they're connected in a way.
They are connected, and that's why they both end up getting charged the same. Exactly. So in this example, we have two independent plates that have been charged somehow. I don't really care how they've been charged. So we have some weighing A to 1 and then A to 2. To find the total electric field then between these two plates, we can't use this because they don't have the same eta. But we can use the fact that each of them individually would be eta over 2 epsilon naught. Okay? So E1, the electric field due to plate 1, we know it's to the right. So E1 is the 40 nanocoulombs per meter squared over 2 times epsilon naught is our constant, 8.85 times 10 to the negative 12 coulombs squared over Newton meter squared. And in this case, it's in the x direction. So you need to put in 10 to the negative 9 for the nano. So E1, the electric field due to plate 1, is 2,260 newtons per coulomb, and it's in the positive x direction. E2, the electric field due to plate 2, we can use the same equation. We're only going to use the magnitude of the surface charge density. Because we already know the direction. So it has a value of 3,390 newtons per coulomb in the x direction. So the total electric field between those two plates is simply the sum of these. (5,650 newtons per coulomb). Now electric field values, just to give you an idea, this is perfectly fine for electric field. The electric field values can get very, very large. When I brought that Van de Graaff generator in, remember I mentioned if the electric field got big enough, it made the charges jump. So when we were seeing the sparking, that electric field value, I remember it was 10 to the 6th is what it gets to in order to make the charges jump. So 3 million newtons per coulomb would be that electric field. So electric field values can get quite large.